Hey, hello. My name is Mark Neyrinck. It's not obvious how to pronounce that name. So I'm very pleased to be here. And I'm going to talk about cosmic scale, the possibilities of indeterminism on cosmic scales. And I'm going to say, well, this is something I added more recently, galaxies as information repositories or generators. I'm going to say that's something I've been thinking about more recently. It has to do with, as Nicolas said, indeterminism is a sort of generation of information. So, right, well, this doesn't need much further explanation, but yeah, it's a question: what on earth was encoded in the initial conditions at the Big Bang? Was this presentation encoded? I think it's unlikely, but it's hard to prove that. And an example of an indeterministic thing is the COVID pandemic. Most likely, there's some small probability of a pandemic each year, but the details of what exactly happened are the result of a lot of things that at least seem like randomness. We can all think of many things that could have produced that. Mutations from cosmic rays, which are quite those are some cosmic things that are pretty random. These particles fly around the galaxy, produced by quantum nuclear reactions in stars, and fly around in a very random way. Maybe if there were animal decisions, people's decisions, that could have produced some the pandemic as it happened. Yeah, I don't need to list much more. But there's of course was a feedback on of the pandemic, not just on people but on the world. I mean, here's a picture of January 2020 and February 2020, the sort of pollution in different parts of China. Of course, during the lockdown, there was much less pollution, so that affected other beings on the planet too. Okay, so I think it's at least a fair guess that some things on Earth are not predetermined by the Big Bang. Of course, so it's possible to disagree with that. It's hard to prove that wasn't prescribed in the Big Bang, but I think it's definitely a good question. Nicolas questioning whether all of the wave structure was encoded in the Big Bang. It seemed unlikely to me. But the question is, or one of my main questions here is, how far do you have to go out in scale before you reach something that is deterministic? So was the solar system prescribed in the primordial universe? That seems more likely than the waves on the beach, but it's actually not totally clear. If you zoom out to the galaxy, it starts to be more likely that it was that at least some properties of the galaxy were prescribed in the initial conditions. But still, actually, it's not totally the structure of the galaxy. I'm going to say it's not totally clear how prescribed that was. And then what about extragalactic scales? So this is kind of my specialty in cosmology, the so-called large-scale structure of the galaxies and the matter in the universe. And at some point, I think we do reach a point where things become deterministic from the initial conditions. So this is a cosmological simulation, the illustrious TNG simulation. So I'm going to say something about the dynamics of what produces this structure. That's pretty relevant. And I'm not going to, there's an easier question to ask about chaos, where the universe is chaotic, it becomes less, well, it becomes more open to interpretation if you get into indeterminism at least, but chaos is an easier question to address. So so there is actually a sort of randomness that we commonly think of in cosmology, which we don't, well, so Nicola said that there isn't really quantum interaction on cosmic scales, and that's true, but actually we do think that that there was a primordial pattern of fluctuations that was once a quantum phenomenon during the Big Bang. So it was generated that this quantum randomness was generated during the Big Bang during inflation, when the universe was much contracted from its current state. And so this is a plot of our sort of random field. It's a Gaussian random field, which doesn't really matter for these purposes, but there's some blue spots and some red spots. The blue spots have less matter, a little bit less matter, and the red spots have a little bit more matter. And gravity draws the red regions together and the blue regions apart. So here's a little video which shows what happens. This is on top of the cosmic expansion also. So you can imagine I'm going to show something in the next slide that describes this, but this is a so-called co-moving simulation where you take out the expansion of the universe and you just look at what happens on top of that. So the blue regions expand faster than the average, and the red ones expand slower, and in fact turn around and collapse and form galaxies. So there's actually, whoops, that's not right. So here's a real-time sort of simulation of a universe expanding. This starts with imagining a very small part of the universe which is expanding, and you see that the stuff is expanding into kind of a void, but well, we think that the universe was homogeneous, not like a sphere with vacuum around it. But even though on the whole this thing is expanding, you get some formation of structure in there. These are sort of galaxies that just form because of gravity.
So this is simulated by a lot of pieces of matter that are kind of the pixels here, and then gravitational interaction.
Yeah, it's just gravity. So I think I actually don't know the details of how they did this, but if this were proper gravity, actually there would be some motions inside these things. There must be some way that they dampened the gravitational interactions within the galaxies. But yeah, this is just gravity that forms these objects. And so I'm going, so yeah, these red things are galaxies, but they're the regions between the galaxies are not completely evacuated. There's still some matter there, just much less matter, and those are called the voids. So gravity is the main thing that happens, but of course that's not all that happens everywhere. A lot of the complication in cosmology happens because, well, the gravity is really easy to model, at least in principle, and that gives these pictures that are labeled dark matter, the pink regions in different models. But the actual the stars and the pattern, the structure of gas, which we can actually observe much more easily than the dark matter is governed by some very traditional well, hydrodynamics. So there's pressure, there's well, there in star formation, there is a lot of physics that comes in. And what happens, is there sort of a pointer thing, I guess? Okay.
How about this?
You can't do this. Right. It's okay. So
Finger works.
huh?
The finger, I think.
Okay, so compared to the dark matter, which is
An extended finger there. No, no, on the right-hand side of the board, the whiteboard.
oh wow, okay.
It's a bit classical.
So this is dark matter under this whole dark matter model, which has been kind of the default model. It has a fairly small scale structure and it's quite clumpy. It has these clumps that are called halos. On top of that, there's gas dynamics, which produces sort of a smooth version of that. I guess it's a little bit analogous to what would have, well, in a room, of course, if you put lots of clumps of gas in a room, they kind of homogenize. And so you end up with sort of a smooth version of that. And then the stars form where the gas is densest, basically. So there's a lot of modeling that goes into this that is, at least in the way it's numerically implemented, has some stochasticity. There's also uncertainty in the cosmological model, even though actually we've made a lot of progress in the last 20, 30 years. We now think we have a pretty good working model of how structure forms. We don't actually know whether the universe looks like this in dark matter, or if it's much smoother, if it looks more like this. This is kind of an extreme version of what it might look like. It's probably slightly excluded observationally, but in principle, you could have quite smooth dark matter, which sort of has less primordial information. And I'll say more about that. But the point of this is just to tell you that about this process of smoothing the purely gravitational system that produces the gas distribution in the universe. Okay, and there's also some ambiguity, I think, in whether we're allowed to, how much of the primordial information we're allowed to consider in the evolution of sort of the flow of the information as the cosmos evolves. So cosmologists, at least, usually think of the primordial density field as the initial conditions, that you specify the density on a grid and evolve that forward, and that gives you some structure. But of course, there's somewhat more information in there in principle. There are thermal motions in the dark matter particles. We think, well, if the dark matter is made of particles, which we think it is, and in the gas, I think it's not entirely clear. Well, at least it's not clear to me whether we're allowed to take the motions of the thermal, like Brownian motion sorts of motions in the gas as the initial conditions. And I think the answer of whether there's indeterminism depends somewhat on that. I don't know if anyone has any thoughts about that. You could well, we can talk about it. Now, if you coarse grain if you set up a density grid, as we usually do in cosmology, doesn't have ridiculously small cells, then that's called coarse graining. And but it's kind of subjective to only look at the density and position space as the coarse graining process. If you coarse grain also the velocity dimensions, then you have more information. But I think so. It's subjective. I think it's more subjective than it should be, at least in my mind, what the initial conditions consist of. But I'm going to assume for this talk, at least, that the initial conditions consist of a density field that was primordial and was generated, say, during inflation. And once the way that evolves, I've already showed a couple of movies of the evolution of structure. It actually helps to understand what happens there to know about this thing called the separate universe approximation. So in the separate universe approximation, it's you can just consider the universe as a collection of, say, balloons that inflate with different speeds, and that's set by the gravitational potential. And these balloons run into each other and occasionally become non-spherical. So you can see there starts to be a shape there that's not circular. It actually works quite well to consider each of these things as a separate Friedman Robertson Walker universe that is basically set by the density in that patch, with a little bit of correction from the tidal field from other stuff, but actually that's a lot of it is basically set by the local density or the local potential. And when you know
separate universe that has nothing to do with, let's say, many worlds, has nothing to do also with these many universes of string theory. This is really
right, so, yeah,
they live in a big universe, and you have mini universes inside the big universe.
Yeah, a lot of little patches, and this shows what happens more realistically when you have a bunch of these little patches that are expanding at different rates. These things, so that these patches are expanding faster and these are slower, and some of them actually collapse to form galaxies. And as you keep going, this is a very simple model that's called the Adhesion Model that turns out to be pretty accurate, actually. You end up with this tessellation of cells of these balloons that are running into each other, basically. And it's all very deterministic, at least in these low density regions. And here's another plot which shows something about the relation. Well, this addresses something about computability, which at least a couple of you have thought about in this kind of context. So the very low density regions are much more computable. They require less computation to predict than the high density regions. So what I'm showing here is kind of a ground truth of the physics that happen to these big particles on large scales. This is the cosmic web here, which is the collapsed regions are shown in pink. And the void regions, the much less dense regions are shown in black. You can so this is n body, which is kind of the ground truth, compared to a simple approximation that is much faster than running the full gravitational simulation. You can you can kind of see maybe that the black particles look very similar between these two pictures, which visually at least tells you that it's rather easy to predict from one to the other. Whereas in the pink regions, this one-step approximation doesn't do very well. And so in those regions, you do need to use something like an n-body, much more computation to predict the structure. So there is also a link between determinism and computability that comes in here. But it's this is kind of an argument, one argument for why the determinism is stronger in these.
Understand. So this is a 2D.
Yeah.
You compute it 3D and then you project, or what is that?
Yeah. Yeah, it's actually a 2D slice of particles from a 3D box of particles. And there are other ways to understand why things are pretty simple in these void regions. Maybe I should say what this is on before that. This is another way of looking at the matter in the universe, looking at the matter between particles instead of the particles themselves in a simulation. I won't get into the details, but it's basically it treats the matter as a deforming mesh instead of a bunch of particles. And this is actually more accurate in a lot of ways. And you can see that, well, it's pretty, I think it's prettier than the usual particles. But you can see that there are some places where there are folds. This is kind of like a fabric that can be folded. This is actually a two-dimensional simulation where, you can see that there's kind of a fabric that stretches in some places and becomes less dense. Those are these lighter regions, the voids, and then there's the cosmic web, which consists of these folded regions, and what we kind of measured was that the chaos is negligible. It's basically no chaos in these unfolded regions, but there is chaos in these folded regions. And you can understand this in a few ways. One is that chaos is often, at least astronomically, is linked to dynamical processes. There are dynamical timescales that come in if particles are crossing each other on some timescale. That's what we call a dynamical time. But if particles are not crossing each other, if they're just expanding, then there's no crossing time. And so the chaos sort of develops on one of these dynamical timescales. So if there is no dynamical timescale, there is no chaos. And that's what happens out here. Whereas there can be very short timescales as you get to higher density.
We have still some questions. I guess we are allowed to interrupt, no?
Oh, yeah, of course.
So here you're talking about, these dynamical models. You said it's a gravitational interaction. Now you have also dark matter. How do you model that? And is that really how relevant is relativity here, or can you just ignore relativity and use a Newtonian instantaneous, gravitational interaction in the model?
So there isn't true relativity here. The general relativity does kind of come in with the expansion of the universe. But besides this is just Newtonian gravity, basically.
It's Newtonian gravity.
Mm-hmm.
And dark matter, how do you model that?
Well, so the dark matter is, the answer is not really in detail. The dark matter for cosmology is just matter that interacts only gravitationally. So saying that this is a dark matter simulation. I'm not actually getting into the details of the dark matter. I'm just saying that this, for a cosmologist, that just means that we're only simulating gravity. That we don't simulate the pressure, hydrodynamic pressure, or other physics.
I can just erase and forget dark matter each time it is mentioned.
Yeah.
Is that what you're saying?
Yeah. Basically, yeah. I mean, no, it does mean something, but yeah, I'm using some jargon, unfortunately. Dark matter, I don't know, does dark, yeah.
It appears at several, here
Right,
and
so-
also
so
the
here-
last
yeah,
one.
so it does matter. Dark matter matters. This kind of structure that appears, these pleats in the sort of fabric, those do depend on this being dark matter and being collisionless fluid, or actually arguably not even a fluid because it can be multi-stream.
So dark matter again interacts with gravity, with
only
maybe a
gravity.
negative sign somewhere. Or?
No, it's purely gravitational physics. That's what I mean by dark matter for these purposes. And so.
So what you plot here is all what is not dark matter.
This is just dark matter.
This is just dark matter.
Yes. So you don't get as sharp features. So, right, in reality, there would be gas also, gas in addition to the dark matter, and that wouldn't form these sharp, as so-called caustics. The same term that's used in optics
I still don't understand what how do you simulate dark matter? There must be a difference between dark matter and non-dark matter.
Yes.
Matter. So what is the difference in your simulation?
in the simulate. Well, so dark matter and for these simulations is purely gravitationally interacting. The non-dark matter, which this simulation doesn't contain, but this simulation did contain. The non-dark matter is the gas, for example. So in the case of the gas, there's pressure and well, temperature and other hydrodynamical forces in the Euler equation. Or
so for the gas, you have additional forces which are not purely gravitational.
right. And those so the gas forms shocks, and that's actually a source of randomness and some possibly, whereas the dark matter, at least in principle, is purely deterministic. So that's quite important actually. So in the case of the gas, that of course interacts with gravity, but then you can't have different streams of gas going in different directions at the same position. They actually collide with each other. Whereas the dark matter is collisionless, so different patches of dark matter can slide through each other without.
But dark matter and matter also interact gravitationally.
Yes.
Thank you.
Yeah.
Can I just ask, since we've broken, I'm trying to understand how you're thinking about determinism here. I mean, you have issues of actually computing something. And, you know, as you say, okay, you're going to coarse grain some stuff. You're going to use these approximations, like saying a little patch is Robertson, Friedman, Walker, when it really isn't. You know, we all know it isn't, right? That's just a tremendous simplification. You can get chaos. Of course, the standard examples of chaotic dynamics are fundamentally deterministic, right? Fundamentally deterministic. And you get transitions from laminar flow to chaotic dynamics. We understand all that. But I don't understand why. I don't understand how you're thinking when you say, oh, this is deterministic and this isn't. Okay. Are you just talking about how good a computational approximation is? I mean, that's not a fundamental, that's just a very constrained, that's what you can do with some limited tools in trying to model a system that everybody knows, no matter what your views about anything, is much more complex than what you're modeling, right? So what is it you mean when you say this is deterministic, this isn't?
Well, I haven't. I guess I must have been a bit sloppy. I haven't actually shown that anything is not deterministic here yet.
Yeah, but at certain points you point, you say, well, this is deterministic, right? So
No, you said random. You said random, not
well, the word deterministic, I mean,
deterministic and
all on
random.
tape, but I'm just, it doesn't matter. Yeah, like this, okay, you've got, you say the n body thing is more like the precise solution, although that's obviously got a lot of approximations in it. The one-step approximation is some quick and dirty thing that's doing pretty well in some regimes and not so well in other regimes.
Yeah.
But at a fundamental level, do you think that that has anything to do with whether the world is fundamentally deterministic?
Not necessarily. I do think that where the amount of computation that's necessary to predict something is high, that often a lot of processes come in that could produce one would be more likely to find indeterminism there than otherwise. But for this picture, there's no indeterminism really. It's all gravitational Newtonian gravity pushing around some particles, which is deterministic. Now as the gas comes in, that becomes questionable whether to what degree the fine scale structure here is purely deterministic. And that also is because there are processes that couple very small scales to larger scales. So, well, I'm going to go on but I'll come back to these things. So this shows some chaos in galaxies. So this is from a paper by Shai Ganal that I later wrote the paper on a couple of years ago, or that I'm going to show also. But what they showed in this paper is what happened when very small perturbations were put into positions in a cosmological simulation, and they saw that well, some perturbations grew from a very early time to almost the current time, and the galaxy looks different. So what they did was they took a simulation at this early time and just put very tiny position perturbations, 1 part in 10 to the 15 machine precision perturbations, and tracked those. And yeah, there's some chaos in the galaxy structure. This is, but it's unclear to what degree this is physical chaos or leading into determinism. In the numerical simulation, there were some explicitly stochastic events that happened. The major one of those is called an AGN. It stands for active galactic nucleus, and that is a process in which the black hole in the center of the galaxy some matter falls onto that black hole, and the black hole shoots out other matter, and possibly, so this is a coupling between small and large scales that I was talking about. And I think that it's not clear whether that could have some stochasticity associated with it or not. But at least this is a high degree of chaos. And if there's a tiny amount of stochasticity introduced somewhere, that chaos could produce a indeterminism on larger scales than the very small scales that the indeterminacy came from. So just to say a little bit about what I did with them. This is the same person, Janelle. What we showed is just that the amount of the separations between particles in that simulation become very large in galaxies, so that these red blotches are galaxies. And the color scale here shows the physical separations between particles between the perturbed and unperturbed simulations. So basically the particles get separated on the scale of the galaxy itself, whereas if out here in the underdense regions, in the very low density regions, there's very little separation between the perturbed and unperturbed simulations. And also another thing that we showed was that, or we found, we weren't really setting out to show this, but we were a little bit surprised to find that even some outflows of gas from the galaxies, which happen similar, well, basically from these ADNs that I just mentioned, where a black hole shoots gas in a jet outside the galaxy. Even in that case, that also didn't incite turbulence or chaos outside the galaxy. So if there is some, well, the chaos kind of stays constrained within the galaxy, even if there are outflows of gas. And this is just a plot showing a factor of a million in some units, showing the difference in the separations inside and outside of the galaxy. And so now these few slides are about possible sources of indeterminism that could arise in the galaxy. So I guess we may not have a talk about spontaneous stochasticity until Wednesday and remotely, but this is a kind of a topic that's related to so-called spontaneous stochasticity, which was found almost 100 years ago by Richardson. This is called anomalous diffusion, and it has to do with turbulence. What he found was that, don't worry too much about the details of the equation here, but what he found was that he did experiments with weather balloons with various separations, and tracked the separations between these weather balloons. And he found that he looked at the behavior of the separation at early times compared to late times, and found that there's sort of a constant, this A of that's a function of the initial separation between the balloons. And if you take the limit as that initial separation goes to zero, you still get a final separation. So that implies that even if you were able to put the two balloons in the same position initially, you would still get some separation between the balloons, which is strange. So I think apparently, and I'm not an expert in this field, but I think apparently he didn't quite realize or talk about this. It took a few decades for people to think about this in terms of actual stochasticity in the turbulent flow. But this was kind of a precursor of that.
But this is a kind of exchanging two limits. Now you can go to the limit R0 equals 0. So the distance between the initial condition goes to 0. And if you do that first and then let evolve, of course, you have a single initial condition, so it evolves deterministically. But what you do, you let both evolve first, and only at the end for a given time, put the initial condition back to 0, the difference back to 0. And then the evolved solutions don't match.
Yeah.
So depending on in which order you take these two, well, let's call it limits, you get different results. Correct?
Yeah, yeah, I think so. And the reason that I'm mentioning this is that if there were a process like this in play on small scales in the accretion of matter onto a black hole, which produces a jet, here's a picture of that. Well, here's an actual picture of a jet coming out of a galaxy. There's, well, the detailed structure of that jet is it's a turbulent flow, which if turbulence can produce an effective, unpredictable stochasticity, that implies some unpredictability from the initial conditions on galaxy scales, perhaps. And so I think that's the prime example of something that could couple very small scales to, and well, non-astronomical scales even, to the scale of a, say, even a galaxy cluster. That this is this is just a picture of some blobs, but actually it's only this central thing that's a galaxy. This is actually a galaxy cluster with a lot of galaxies. So this is these are huge scales that this jet of material is coming out of. So that's a coupling of very small scales to very large scales. However, even though this is a very large scale, it's not quite the typical intergalactic distance. So it probably doesn't reach much outside of the across a huge void that doesn't have.
So Tim Palmer, sorry.
Yeah.
This is Tim Palmer, the climatologist.
Yeah.
What is he doing here?
Well,
to do with climate.
No, so I just mentioned that because I had an email exchange with him, and he was surprised that or he didn't quite believe that there was a maximum scale of turbulence in the universe. So one of the points of this, which I thought was obvious at first, but it's not, is that there is a kind of a maximum scale of turbulence, which is set just by galaxy sizes. You don't get matter crossing other patches of matter on super large scales that are intergalactic. And so, there is chaos in galaxies, and I should have said that I'm not from the first person to find chaos in galaxies. I mean, that's been known for a long time. So there is chaos and turbulence in galaxies, but not really outside of galaxies. Okay, so that's kind of summarized here. There's high amount of turbulence inside a galaxy. Even in these filaments that aren't galaxies, there is chaos. Maybe some. Well, I haven't actually. I shouldn't be talking about determinism. I don't really know, but if there is some indeterminism within a galaxy from one of these jets comes from a black hole, it's not unlikely also that some with the chaos coupled with this stochasticity in a different region that's outside of a galaxy, but not the lowest density region, there could be some indeterminism there as well. But in the voids, things seem to be totally deterministic.
How could void be as anything else but deterministic? If it's empty, it's empty.
Well, it's not completely empty. There is some stuff there. It's just,
The density is very low compared to the galaxy.
So yeah, I guess I don't necessarily mean to imply that this is surprising. But I think it's not, for someone who hasn't thought about large scale structure, it might be interesting. And not something that they thought about before.
I mean, I found it kind of surprising, just just think of you're doing Newtonian gravity, right? Do Newtonian gravity with 3 point particles, 3. You know, in many cases that will get chaotic.
Yeah.
So the fact that you would ever escape, even if there are big voids between these galaxy clusters or whatever, one might think, sure, it's going to be chaotic.
Tomorrow we have a talk on free body.
But I take it what's going on is that the interactions between these galaxies become so small that it's essentially, it's not getting into the chaotic region.
Yeah, it's the particles, the matter out in the atoms is just generally expanding. And so, there aren't gravitational interactions that go into a chaotic regime. All right, so I am wrapping up, but I wanted to mention something about looking at comparing the primordial information from the density field that arose during inflation, comparing that to the final information. So I think this could be a way to bring some empiricism into this question, at least in principle. I mean, it's not, it's far from a clear program of what to do, but this actually relates back to this separate universe approximation a bit. It seems to be a pretty good approximation to think that the information in a patch that collapses to form a galaxy, which is called a protohalo, that the information is kind of stays contained within that patch throughout the universe's expansion and the formation of the galaxy. So here, so I think it's interesting to look at the amount of information that's within such a patch. This is in a few different models of dark matter with different amounts of small scale structure. The patch that would form the galaxy in a ridiculously smooth model that's been excluded, it would look like this. So you have, it becomes ambiguous exactly how to quantify the information in this patch, but I think it doesn't really make sense to think of all of the structure in the Milky Way, including the structure on Earth, that's coming from this very smooth patch, that there would have to be some additional information generated somehow. Now that could, as I said in the first couple of slides, that could be from some thermal motions in the gas or something, but at least this density field, it doesn't make much sense to get the structure in the galaxy from this very smooth patch. We do think that the initial patch had more structure on small scales, but kind of crude counting of this information that I made a few years ago estimated that and if the patch looked like this, there would be 30 gigabytes of information that would produce the whole galaxy, which seems pretty ridiculous. Even something that's at the border of being excluded by other more conventional observational techniques has 4 terabytes of information in the galaxy, which we have in this room. We have much more than 4 terabytes of data on hard drives. But a more realistic model, sort of a fiducial model as of several years ago, you might have 10 to the 25 bytes, which starts to be large enough to seem like it's plausible, but it still is kind of not as large as it could be. So if you consider that there might be 1 bit per Planck mass in the protohalo, you get 10 to the 50 bits, which is pretty big. Another Planck scale sort of calculation gives 10 to the 55 bits, which is kind of in the same ballpark as that. Not expecting you to have read that in detail, but that starts to be an appreciable amount of information. But it becomes ambiguous how to compare that to the information in the galaxy or even on the Earth. I don't know how you would quantify the amount of information on Earth. There is a case where we do know how to quantify information in a kind of rigorous way, and that's for black holes. The Milky Way's black hole has like 10 to the 90 bits of information, which comes from Bekenstein-Hawking and entropy ideas. If you're not if you don't know about that, I can say a few more words about it, but it comes from considering the black hole as a thermodynamic entity, and if you count the number of microstates that could have become a black hole, you can think about that in terms of a sort of information, and you get this number 10 to the 90 bits. And so if you knew that there had to be that much information that is contained in a black hole, if you know that would imply that information was generated in producing that black hole if the galaxy contains only 10 to the 50, at most 10 to the 50 bits. I don't know if I'm making sense here, but you don't know that there has to be that much information in a black hole, because very simple situations can form a black hole. You could have a very smooth distribution of matter that is specified by not very much information, much less than 10 to the 90 bits of information that can collapse to form a black hole. So it's kind of like a hard drive that only has a few bits on it, and otherwise is empty. And I think it would be curious if black holes typically were nearly empty of information, not it's not a situation that would be impossible, but I don't know, that just seems odd to me if black holes typically didn't have very much of information compared to what they could have. And if black holes did have typically more than a few bits out of 10 to the 90 of information inside them, that would imply that there would have been some indeterminism. That would imply that information was generated at some point during the formation of the black hole, and that would be a suggestion for indeterminism happening. And I am going to end quite soon, but I just wanted to say that some scaling relations between the masses of black holes and the masses of galaxies that they come from are known. And generally, the mass of the black hole is larger for a larger galaxy or a larger dark matter halo in a way that is kind of reminds me of the way information is generated in cities. So I don't know if you have heard of this. I hadn't heard about this years ago, but if you look at the amount of information, which could mean a lot of things, that's in a city. So for example, well, some academics did this. So looking at academic information was one thing they thought of. So they were looking at neuroscience papers, I believe, and you get a disproportionate amount of neuroscience papers written in a high density or a high population area. Sorry, this is US centric. You get a power law of comparing the population to the number of neuroscience publications that has an index of 1.87, but this is a generally found thing that if you think of something that you could interpret as information in cities, you get disproportionately more interaction and generation of information, the larger it is. And there's a suggestion that I think, well, you get disproportionately larger black holes, at least to some point in a large galaxy compared to a smaller galaxy. So if a black hole is some measure of the amount of information in a galaxy, which is very speculative, that would be some kind of suggestion that information is generated more in large galaxies than smaller galaxies. So actually, that was my last slide. So thank you very much. And of course, questions are very welcome.
So could it be that concerning chaos in the regions and in the voids, that in the voids there's still chaos, but maybe on a much longer time scale? Or do you really mean there's no exponential response in the regions?
I think not. At least in the lambda CDM, which is jargon, but in the accelerating dark energy model, where the universe is accelerating in its expansion, these patches will remain as they are. Basically, after you subtract the expansion, and they will never be chaotic. And of course, well, if there's an alternative model where things collapse again, which is unlikely, then that's wrong. But no, I think that they're always going to be deterministic. Sorry, I was conflating determinism and laminar flows again there, but I mean I mean, they will always be non-chaotic.
So I have a question about, so the workshop, our workshop is varieties of indeterminism. So I guess we are going to use a different meaning for this term. So I didn't exactly get, in your case, I believe you were using chaotic evolution all the time with the quantum term. So from a physical perspective, I would say everything is deterministic. But apparently my vision is too naive. And what do you exactly mean by indeterminism? It's not randomness, I guess. I didn't get, so you can.
So, right, there were no quantum interactions happening here. There are suggestions. So I was suggesting that that there could be some the sort of unpredictability that happens in very chaotic systems could be identified with indeterminism. In particular, when you have a coupling, a very small scale process that even could have some quantum interactions on some maybe at a very low level. So these environments around black holes are very energetic and reach, well, certainly for astronomical standards, small scales. And I think it's not, it's plausible to me that a little bit of indeterminism could be generated through quantum indeterminacy. It's somewhere in the accretion disk that it produces one of these jets around a black hole. So I think it's not clear that that's actually happening, but I think it's worth asking the question of whether there could be some quantum processes in the generation of one of these jets around a black hole that could have a small, I don't know, even a tiny amount of quantum indeterminacy can produce a large difference. So I think it's not clear whether that's. I think it's worth asking the question of whether that is happening.
Can I summarize saying, like, okay, you believe that there is in a small scale for a quantum process, and then this initial indeterminism of quantum origin gets amplified because of chaotic behavior.
Yeah.
This is what you're.
Yes. Yeah.
Tomorrow I will argue that classical chaotic dynamical systems can also be considered as indeterministic. Determinism is not necessary.
I think we would do well, just because there's a lot of different concepts floating around here, to sort of standardize terminology. I mean, you want to talk about chaos and non-chaotic systems. We all know you can do that in deterministic. It's originally done in deterministic settings. If you're talking about chaos, let's talk about chaos, or, exponential divergence of nearby initial states, and not assume, right? I mean, whether that means anything about determinism, indeterminism, we can have arguments about, but they shouldn't be prejudged by the terminology.
I didn't mean to suggest.
Yeah, no, I understand. I mean, we also just do have to appreciate some of the different things. I mean, you mentioned the Hawking stuff about, how much information can a black hole contain. That's a really weird conceptually what's going on. I mean, mostly you're using even Newton, but if you're using GR, a black hole contains infinite amount of information. It can have any mass on the real number scale. Classically, it can have any mass. Specifying that mass is an infinite amount of information measured in bits, period. So if you say black holes can only contain so much information, you're already doing something that's in a different regime than the theory you're using to do these calculations. So we just need to see what's coming from where, right?
Yeah, I think indeed this terminology is very important. But maybe at the end of the day, or maybe tomorrow, we can try to start figuring out what the different words mean really.
Yeah, it sounds like a good idea to let more things be on the table before you try to sort them out.
Maybe, okay, we're already late, but the chairman is not saying anything, so
I take a last question. You want to add something? Yeah.
yeah, but so dark matter seems to be very important here, no? Because you mentioned it every second slide or every slide. But of course, 20 years ago, people were already simulating the dynamics of cosmic dynamics. But 20 years ago, there were no dark matter in the models. Or maybe it's 30 years ago that there were no dark matter in the models. So did the models 30 years ago not agree with the observation, or?
Yeah, basically they didn't, there wasn't a model that worked well enough to.
Because my understanding is that dark matter was necessary essentially to explain that the speed of rotation of galaxies and things like that, but not for the big structure, the intergalactic structure.
Well, it is. I guess it became okay. This doesn't really matter, but it became pretty well established in the 80s that dark matter is necessary not just for galaxies but for galaxy clusters. And then as there was a concordance cosmological model including dark energy also. There are many places where it's clear that you need dark matter. It's necessary to produce the observations of the cosmic microwave background.
So that was already in the 80s.
Yeah.
It's more recent.
And then it was-
Okay, anyway, so I think maybe.
Yeah, so let's thank again, Mark.